Hey everyone, welcome to this video lesson. It's the first time I've done one of these, so you'll have to forgive me if it's a little rough around the edges. But like the subject we're doing, it's a learning experience. Now today, I'm really looking at going over relative atomic mass. Now, the first time I was taught this part of the syllabus, I was so confused. Like genuinely confused. The second time I did it, a little bit later, I was a little bit older, had a different teacher, it seemed to make absolute sense. Now, I didn't know what had changed in the meantime, but it looked like something had, so I'm going to try and recreate for you today the second of those experiences and help you try to understand relative atomic mass and what it's actually relative to. So, you'll have all seen your periodic table by now, and the periodic table you use, I've got to say, is a slightly simplified version. Now, don't you worry about that, because a very good chemist and teacher once told me, the thing about chemistry is they always tell you the lies first, and then they tell you the truth, which is way more complicated. Now, what he meant by that is this. Sometimes in teaching and learning, you need to be able to access information at a certain level so you can get the teaching process accomplished, and then with that foundation of understanding you can go on to the more complicated version. So really what you're looking at is facilitating your access to understanding. So your periodic table that you'll have seen looks like this. Carbon 12, for instance. That's where we're going to start today, and there's a very good reason that we're going to start there, and we'll explore that later. Hydrogen, hopefully that's familiar to you, and last one here, magnesium, 12, 24. And you'll have been told by your teacher what these numbers mean. 6, number of protons, right? 12, number of protons and neutrons. And we can work out some things from that. But if you look more carefully, on the section of your periodic table where it tells you what the names of these two numbers are, it will tell you this is called relative atomic mass. Now, a lot of people kind of seem to really skip over that a bit or not go into too much detail. And it was that bit of detail that I struggled on the first time. But this is very important. So, relative atomic mass has to mean that we are relative to something. One thing is relative to something else. So what is that something? This does not mean each magnesium weighs 24, well, it's not going to be grams, it's not kilograms, it's not any of our usual methods of understanding mass. What we've got here is the relative atomic mass is relative to, like you may have put together, the number of neutrons and protons. Now, this is where we come on to carbon 12. And this is the interesting bit. If you take a sample of these elements, you don't actually get a pure sample. When you take your sample, there'll be a high percentage, the overall percentage will be atoms containing 6 protons and 12 protons and neutrons, something like that, 1 proton, or 12 protons and neutrons. Overwhelming, but not all. You will also get a sample of isotopes. Now, I'll give you a second there to try and recall what an isotope is. Now, an isotope is a chemically identical, so that means in nature they react exactly the same as their kind of parent or the element that we see on our periodic table, but they have a difference. And if you've remembered it by now, the difference is up here. No, it's not, it's down here. It's down here. They have a greater number of neutrons. Same number of protons, that's how we know what element they are, and that's why the periodic table goes in in numerical order of number of protons there. So we know what element they are, but they have a different number down here because they have extra neutrons. So carbon-12 in nature is the purest of those elements, which means if I take a sample of carbon-12, what I get is 98.93% of that sample will consist of these atoms here. So a very small percentage will be isotopes, and you might have heard of some of those. Carbon-14 that we use for carbon radio dating, yeah? So when we were defining the atomic mass unit, people thought, right, well, this will be our standard to be relative to, okay? The standard that we're going to be relative to. Because this one gives us the closest mass to an actual purest substance. And we've got 12 protons and neutrons, and the atomic mass unit came out. We decided, right, well, we'll call that one 12. So carbon has a relative atomic mass of 12. Now, this is where kind of the lie begins a little bit, because over time, these units like this and definitions, they change and they evolve, and the better we become at measuring things, the more they evolve and they change slightly. So this is what we're being taught right now, and this is great, but what you'll find as you go on and learn more chemistry, you'll get kind of closer to a more refined definition of how these things are found in modern day. You're also talking about your periodic table. I said it was a little bit simplified. What you're going to find, especially in the next 2 years, is that these numbers here will actually be quoted to about 2 decimal places. So these are no longer exact numbers, and that's all part of redefining, which is what science is, right? We find more information. As the information comes in, we change, we grow, we accept. So, what we came up with, what's the important thing for you? What was the thing that kind of confused me when I was first learning this? Well, it was as soon as they got to a fraction. I was like, fractions now? So, but it's not too difficult. If we decide, through our definition, that carbon has a relative atomic mass which is equal to its number of protons and neutrons, so we say 12, and we compare everything as being relative to that number, what we can then do is define one atomic mass unit. And one atomic mass unit will just be 1/12 of the atomic mass of carbon-12. So if carbon has 12 units, obviously one atomic mass unit will be equal to 1/12 of this value. So some of you are probably saying, whoa. You forgot the electrons, Mr. Brough. Well, I kind of didn't forget the electrons. The electrons aren't actually being used in this calculation for this definition. And there's a good reason for that. First reason is their mass is much smaller. So it's kind of less significant there. But even more than that, this is not the actual mass of an atom. If you were calculating the mass of an individual atom, you would find it in those kilogram units. You know, there's other units as well that we use. But if you wanted to know the exact mass, it would be slightly different. And what you would do for that is you would add up the mass of the number of electrons and the number of neutrons and the number of protons. But there's an issue there. And you'll get onto this at a later date. And this is like mind-blowing. It's a great piece of science. And I'll just go into it for 1 second now, right? Won't be on the test or anything. When protons, neutrons, and electrons are together in an atom, they have less mass than if they were all individuals. Yeah, I'll tell you that one, right? Just say that one more time because it's a bit mind-blowing. If I had 12 electrons, 12 protons, and 12 neutrons, so now we're talking about magnesium. Okay, so an atom of magnesium, 12 electrons, 12 neutrons, 12 protons, and took their mass I would get a number. If they were all put together to form an atom of magnesium, the mass would be different. And that's down to something called binding energy. But like I said, that's just a side note. Okay? Don't let that confuse you. It's just a piece of kind of information for next time. Now, so we're not ignoring the electrons. That was by design. So one atomic mass unit is 12. 1/12 of the atomic mass of carbon-12. We can make some relative calculations. Magnesium, an atom of magnesium is twice the mass of an atom of carbon-12. So its relative atomic mass of carbon-12, that needs to be 24. Twice the mass, twice the number. Hydrogen here, that's really interesting too, because that is 1/12 the mass of carbon. So it's one atomic mass unit. Seems simple, right? Okay, so we'll move on then. So, on your periodic table, you have all of these things already calculated for you, already there. The biggest thing to remember is that this is not just the number of protons and neutrons, this is the relative atomic mass, and a simple question will be, on a test, on an exam, what's the definition? Essentially saying relative to what? So, now, here's something that's interesting too. Try to calculate the following relative molecular masses I've put up here. What does that mean? Well, first question, I guess, is do the same similar rules apply, or do these rules apply to create for the mass of a molecule? Because there we get somewhere interesting. And I've just remembered, I've missed something out, haven't I? Here we go. Let me get a pen. Be back in a second. Chlorine, 17, 35.5. Yeah. Now, as far as I can remember, but don't quote me on this, you go and check that periodic table for yourself. This is the only one you get on your periodic table which has a decimal place. And why is that? Well, in the same way that carbon-12 has very low percentage of isotopes of carbon-12, chlorine has a significant percentage of chlorine isotopes. It's basically split up into roughly 75% of Cl, chlorine 35 atoms, and 25% of chlorine 37. And when the ratios are that big, then you do need to factor those in. So, and this is a clue to where we're just about to go, okay? So, if we were doing this calculation, it's straightforward, it's just like you'd use ratios, okay? So bear with me. You've got 75 over 100, or 0.75, times 35, that's coming from up there. So 75% of that number, plus, and I'm sure you can guess now, 25% of that number times 37. And if you do that calculation on your calculator, you come out and find you've got a relative atomic mass of 35.5, which gives us this there. All right? Lucky I remembered that. Let's put a bit of a box around this to denote that that's a bit of a side point from where we're going now. Now, this is where you get to do some work. Do these rules work if you were to find the mass or the relative atomic mass of a molecule? Well, actually, the answer is yes, they do. And I'm thinking that just using logical progression and your own initiative, that you can work this out. So, we've got NaCl here. Let's go back over this side of the board. NaCl. have a look on your periodic table. You'll see Na, sodium, and chlorine, and you'll see the atomic masses. Have a guess at what the molecular mass would be. And if you want to stop the video, you can stop the video now, try and work it out. When you come back, we'll go through the answer and you can see if you're correct. Okay, you're back? Great. So, NaCl, we've got Na, you should have found, let me get over this side, try and do this for you. Na, 23, plus Cl, 35.5, and what do? We add those together, yeah? So, NaCl will have a relative molecular mass of 58.5. Okay? So, 58.5, this together, this molecule here, 58.5 times bigger, heavier than a hydrogen. It's good, isn't it? Let's try a couple more. Here we go. Let's see if we can confuse you a bit. Let's see how well you're doing. We'll go H2O, and then if you really like a challenge, how about this one? Magnesium nitrate, MgNO3, 2. If you want to stop the video now, you can stop the video, and we'll come back and we'll do all these together. Hey everyone, welcome back. So, hope you had a go at those two molecules that we were going to calculate, H2O, MgNO3, 2. Let's see how you did. So, H2O, water, always a favorite with examiners at this level. Don't forget, 2 hydrogen atoms combining with 1 oxygen. So in this case, we have 2 times the relative atomic mass, 1, plus 1 times the relative atomic mass of oxygen, 16. So 2 plus 16 gives us 18. I'm pretty sure a lot of you got that one. How about this one though? MgNO3, well, what's Mr. Brough done? There's a 2 down there. 1 times 24, that's the magnesium. The N in brackets, which means we've got 2 nitrate molecules here. So that's 2 N's, 2 times 14. And how many oxygens have we got there? Did everyone work this one out? We've got 3 oxygens. Take this out of the way. 3 oxygens times 2, 6 oxygen molecules, 6 oxygen atoms, 6 times 16 gives us a total here of 148. That's calculation of molecular mass. If I was to take a guess, I'd say these calculations here are most likely to be the ones that you'll have to do in the future, as well as the definition there. Hopefully this really clarifies a little bit of your understanding and the nature of what relative atomic mass is, because after this one, you go into Avogadro's number on the mole, and it will really be helpful if you have this one really solidified in your mind, because that's another step. Okay? Until next time then, don't blow anything up.
How do you think that went?
It was nerve-wracking. It was, so I wanted to start off and I was thinking, oh, you know, I'll use like Ray's bit about kind of first you get the line, it's simplified, and then you get the concept in much greater detail once you've got a foundation, so you understand it and you make faster progress. But I was like, just couldn't get those words out in the start. So I guess in future I'd get my intro solidified and probably not try and kind of make any kind of joke or a quote. But I think the essence of what was said was important for people to understand. Yeah, I think it was probably a little, I got perspiration all over my top lip and my knees are shaking. So yeah, it was probably a little bit rough, But I think with some practice, it's the first time I've done something like this. I'm way better without the camera, I guess, or I hope. But I hope it came over. So that's about it.